Good evening from Unigroup Engineering Dyno Room, here with another live feed. Tonight I'm going to cover the topic of camshafts. This one was the one that got asked the most. I've reached out and asked you guys as to what topics you want me to cover, and this one was the one that got the most votes. So what does it all mean? You know, we read about all this stuff: 256 cams, 274s, 262s, 10mm lift, or 228 at 50. You know, this, that, etc. Okay, I'll try to break it all down, showing real life examples. I've got this Toyota Supra behind me. I've just done a cam change on it and a tune, so I'm going to show you how the engines respond to cams, how cams work, and try to give you some information on how to pick camshafts for your own engine, or at least have a bit better idea of what people are talking about when these things get mentioned on camshafts, such as, you know, the 264, 256, etc, etc. I'm using these numbers mostly applicable to Japanese engines, but you know, engines are engines. Camshafts, as long as it's got a camshaft, all these theory that I'm about to show you guys, it all stands. So all right, let's get started. So I'm going to take you over to the car, run you through what it was before, what we had to do, where it is now, and the camshaft changes we've made, and then go from there. I think this one, there's a lot to cover. I'm feeling that it's probably need to be broken into two parts. I'm not sure, because I'm just doing this on the fly, so I'll see how I go. Hopefully, say around 20 minutes, I'll try to wrap it up. Okay, turning the camera around now. All right, Toyota 2JZ. So this one is a fairly standard engine, with the exception of the camshafts and the big turbocharger that's on there. It's got aftermarket engine management system, Haltech Elite. It is running on E85, and later on it is going to go on flex fuel. So on this car, this had a fairly large turbo, so it was actually quite powerful as it was. The complaint was that, you know, it lacks low down torque. Again, it's the sort of thing that you would get. It's a precision, I believe it's 67, 68, so it is quite large. So again, it really didn't do much until 4,500, but once you got there and it came on boost, yeah, it performed quite well and lively, and as you'd expect, it went quite well. So okay, how did we go? Where did we go? Where is this now? Okay, so the where I ended up with this engine is, I'll show you the dyno graph from this car. So I've stopped around this 457 kilowatt mark. So working this out, we're about, you know, 550 plus horsepower at the wheels, so somewhere near 700 horsepower. Fairly is standardish bottom end. And again, this sort of thing, if you are careful and you do it well, you are going to be able to do this on a fairly standard 2JZ Toyota engine without getting yourself into too much trouble. Okay, so how this engine performed and what we're looking at. So I'm starting the runs here around 3,250. I'm taking the engine to about 7,000. Again, stock engine, sort of respecting the stock red line. It can go more. I'm just being extra safe. Again, reliability is key thing. As soon as we break something or we start having problems, fun comes out of it really fast. So again, focusing on reliability as much as I can. So boost wise, I've pulled the paper out a little bit so you can see on the scale here. So that's about 25 psi there, so I'm running about 25 psi. So you can see engine, when it comes to say about 4,000, I'm already making somewhere near 15 psi. That's actually not bad boost response. At that point, at 4,000, we are making somewhere around 210 kilowatts, which is pretty good. Now on the video, unfortunately, I don't know what's changed on Facebook, but I'm not seeing the comments and questions that used to come across, so I'm just going to have to fly through this, and if there's any questions later on, I will reply. Now my battery is running low as well, which is another thing why I should get going with this as quickly as I can, just recording this on my phone. So all right, Power wise, we've ended up there, so peak power somewhere around 62, 6500, and again there was a bit more to be had there. I really wasn't pushing for power. This wasn't the aim, the what we were looking for here. I was more looking at improving this car overall, a bit more power down low, trying to get it to boost a bit earlier. So let's look at some comparisons before and after with the camshafts. Okay, so what I've got here is my green line is the cam with the standard camshafts. So looking at the two curves, I was around 353 kilowatts there, and it was doing that somewhere around 62, 6500, and then I've ended up somewhere around 384 kilowatts. But unfortunately, because I changed cams, the flow through the wastegate and the boost controller, etc., changed, so I wasn't holding the same amount of boost. So I've actually got another 1.5 psi. Went from 17.5 psi boost to 19 psi boost on my red, which is my after curve. So what I've done is I've kind of just projected this curve to where it would have been as a guess as to if it stayed that, if it didn't gain that extra 1.5 psi and the boost stayed exactly the same. So what's happened here is let's take a look after the cam change. Is we've really lost no power down low. Actually, we've gained power both down low, you can see here. So each little box here, so about 15-20 kilowatts there at about 3750, probably again another 10-15 kilowatts there at 4000, 4500. We're just a little bit better by looks like maybe 5-8 kilowatts, and then we're better everywhere. So fitting the cams to this engine looks like we've really lost nothing, and then we've gained we've gained everywhere. Again, when I say everywhere, it's everywhere within the range of this power curve. So if I was to pull this RPM down, I would make a bet that I've probably lost some power, say below 2000. Again, cam changes and going to bigger cams, always a compromise. I think the stock cams on this car is around 230, 240 degrees duration, which we'll come to what all that means. I've got a 256 inlet and a 264 exhaust on this one. So looking at the power here, it achieved exactly what we were going for, because we managed to make power absolutely everywhere. So considering this is a great thing, because let's say we are talking about turbos and upgrading turbos. We can go to a bigger turbo, make more power up top, but that always comes at the expense of lack of response, or we give away something to gain something. So on this case, with these cams and going particularly small cams, we managed to just gain everywhere without giving anything away. All right, so then breaking this down further. So when we're talking camshafts, we get talked about numbers, lifts. What does it all mean? So let me have an attempt at breaking all this down for you guys. So I'm going to walk over here. Here is the camshaft and what it looks like. Let me turn some light on here so we can see a bit better. Okay, so that is what a cam looks like. So obviously we've got one lobe for every valve that it is actuating. So as this cam spins, you've got these lobes which basically pushes down on the buckets. And yeah, there's our stock camshafts out of this 2JZ. So how does it work? How does it push and actuate the valves? Again, I don't want to go into the real engine basics, as most of you guys watching this, you already know your basics. You're more looking for this additional information that's not so easy to come by elsewhere. So let's just dive straight into that. So what I've got here is lift and how it works. So this is our camshaft that you just seen there, the lobe. Okay, and I've got the bucket here, which is this rectangular part here. I've got the valve spring, which basically pushes the bucket right against the base of the cam and keeps it in contact all the time. That's the job of the spring. And then we've got the valve here. So then the cam has this thing called what we call a base circle, which is this circle here. And this lump, so the tip of the camshaft, this difference here, as the cam rotates, is what creates the lift. So coming into this view here, my cam is rotated through about 180 degrees. So now you can see the nose of the cam is actually pushing on the bucket. So in here, my spring's compressed. So my valve's actually further down compared to this one. So my cam's rotating this way, and then let's assume that it's rotated a little bit more. Now the valve's starting to close, so you can see the action of the valve and how it follows the camshaft. So this, again, going through, this is our follower, which follows the camshaft, and this profile ground into this lobe, and we've got our valve spring. And yeah, that's in a nutshell, that's how it all operates. So then how does that help us with the engine? Okay, with the lift, this is our inlet port, a little diagram here. So I've got the arrows, basically our fuel and air mixture coming in. So as the valve lifts, we open the valve and promote fuel and airflow into the cylinder. So you can see here, the more lift we have, basically bigger this opening, and more air and fuel we can flow into the cylinder, and in turn, have more fuel and air to burn, and hence make more power. So typically, more lift the better. Because it is going to open the valve longer. So with camshafts generally, the bigger the lift, the usually better the flow. Comes a point, and some other considerations, just some basic ones without going into too much detail, comes a point where you can have, let's say we had heaps of lift, and imagine our valve was here. Well, our port's now the limiting factor. It doesn't matter how much our valve's opened. So it comes a point where more lift doesn't really do much more for flow. But again, more the merrier in most cases. What's the downside to lift? Well, to open the valve and push it open in this time, it places more stress and strain on the camshaft to get it that far apart and in a given time during the inlet valve event. So normally less the lift, less the wear and tear, less stress and strain on all your working components, less lift. Again, you generally need a softer spring. Again, we look here how the system works. We're working against this spring. If this spring has to be really firm to follow an aggressive cam profile, we are working against much greater forces of this spring. So eventually it's going to, not eventually, I guess it's going to wear much faster than working against a softer spring. So that's the consideration, I guess, when OEM cars are built. They've got a fairly mild sort of profile, and they don't run very firm springs, and the whole thing lasts 200, 300, 400,000 kilometers. That's I guess the pros and cons of having too little or too much lift. The main con is the wear and tear and the valve spring and the mechanical limitations of the setup. So if we look at what the lift curve looks like, so this is what the valve would do. So initially valve's closed, which is this position here, and then as the cam begins to turn here, it picks the valve up. So here it starts to accelerate the valve, and then the valve starts opening, and then we reach a point of peak lift, which happens to be this point here. So coming from here, valve closed, to valve at max lift, is cam spinning through these two positions, I guess between there and there. It's not the exact position, but you can sort of see what happens. So we start here with the valve closed at the 0 position. We get here with the peak lift to this position, and then closing is basically the reverse. Now, while it's opening, most of the force and the load here is on the cam lobe, and then when we're closing, it's the spring that keeps the follower against the camshaft, and as the cam rotates, the valve basically starts to close and then gently lands in the valve seat and then closes up. So that's basically our valve lift. So then this is a cam that's got say a given amount of lift, and if we were to draw one that's got, say, same duration but more lift, duration we'll come to in a minute, so then the curve would look something like this. It'd come up, so then our peak lift would get somewhere here, and then I'll only draw half the curve. You guys follow me, and then you know where the valve's going to basically end up. So when you've got more lift, so what happens is cam has to push much harder. It needs to accelerate the valve a lot faster, so there's a lot more wear and tear. There's a lot more stress and strain on the whole mechanism for high lift. And then the spring on the way down, may as well continue and finish this curve then. So excuse my crappy drawing. So it's coming down, okay, and then closes it. So in this same given time from here to there, so this is our peak lift point, so this is our closing point. Here with the purple line here, the one I've just drawn, the spring needs to be much stronger because we got more lift to cover to close the valve. So that's roughly how valve lift works, which is easier to understand. Now I'm going to have a good crack at explaining the duration and how that affects us. That's a bit more complicated. I've got these drawings again to illustrate. So what I've got here is just the inlet valve event. So I've got basically inlet valve open, piston at top dead center at basically top of its travel, and then as the crank rotates here, and I've got sort of the rotation, and that's now our conrod. Crank rotates, piston descends down the bore. This is about halfway down the bore. So if we look at it here, if that's our crank there, that kind of comes down, and then when the crank's at the bottom, it's gone through a 180-degree turn. Then our conrod's in line with our crank, and the piston's at the bottom of its travel. So the reason I've shown this, you guys are all familiar with this, but I just wanted to highlight the fact of the duration, because cam duration is measured in crank degrees. So what's happened here is, in this example, we've gone from piston from top of the stroke to middle to bottom of the stroke. Our crank has spun through 180 degrees. Okay, so then that means that it's 180 degrees of crank duration. So if we had a camshaft in this case, and the inlet valve opened exactly at this point, at say top dead center, and then closed exactly at this point at bottom dead center, we've got 180 degrees of crank rotation. So our cam would be 180 degrees long, and that's the duration of the cam. So when people refer to 256 cams, 264s, 272, that's what they're referring to. So let's go and look at, say, a 240 degree standardish camshaft. So we know this part was 180 degrees. So how do we add 40 more, or essentially 60 more degrees to get to 260? So how that works is the cam actually begins to open before top dead center. So let's follow this example here. So crank rotates, so it starts to happen here while the piston's still rising before it gets to top dead center. So 20 degrees of rotation there. Piston there is at top dead center. Again, remembering back to these examples and these angles, how they work. That's why I was going through that example. So this part would hopefully make more sense to you guys. And then this part's what we've gone through up just above there, so 180 degrees through there, and then closes 40 degrees after. So if we add all this stuff, all these numbers up here, how many degrees of crank rotation we've gone through, that's our total duration of the camshaft. So we've got 20 degrees here, 180 degrees there. As it comes around, there's our 180, there's our 40 if we did quick maths. So 20 plus 180 is 200, plus another 40 is 240 degrees. So again, so what does it mean then when we got, say, a 260 degree camshaft, which is similar to the ones that's in this car? So in that case, it's same deal, except we opened the valve even earlier. So this time 30 degrees before top dead center instead of 20. Then we've got our 180, and then we've got our 50. So if we add all of them up, so 30, 180, 50, that's our 260. Hopefully my maths is correct. It's getting a bit late at night, but I hope you followed all of that, and that's what that means. So when people are talking about 256 cams, 240 cams, 260, they're referring to the duration of the camshaft, how long it keeps the valves open for. In this example, we've just been talking about the inlet side and the inlet camshaft. Exhaust works exactly the same way, same degrees, it's just the reverse of the process. So if you can follow the inlet, exhaust side will also make sense to you. It's exactly the same theory. Okay, so then we've got duration, and then we've got lift. So these are our, I guess, main two parameters when we're looking at cams. So then, all right, here's the interesting part, is that, yeah, that's all good, the theory is nice, but so how does it affect the engine? So what happens with bigger and smaller cams and degrees and so on? Okay, let me give you some examples of that. Hopefully it'll clarify some of those points. So what I've got here is 4 engine power curves with 4 different camshafts. So down the bottom I've got basically engine RPM. So I'm starting from, say, 3000 RPM. I'm going to 9000 RPM there at the end of the page. So our first one that we're going to look at is, let's say, our 256 degree cam. So we're peaking power here. Now you can see that this cam compared to 272. We're all peaking at different points, and also more importantly at different RPM points. So we look at, say, the 256 cam. This is what it does. So we start with power here, okay, and then 256, that's where we are. So let's say that next size cam up. Again, this is just for argument's sake. This is not an exact size. I'm only doing it to illustrate the point. But let's say we've got a 272 cam. So if we were to go to a 272 cam, what will happen is we will lose power in the bottom end, which is now my red curve. So you can see I've lost power there, but then I've gained some power up the top there. So 272 cam is likely to make more power as long as your turbo and your airflow and your engine supports it, but also it'll happen at a higher RPM. So we're looking at now much higher RPMs, etc. So on this a little bit like picking, going from smaller turbo to a bigger turbo. We've got more top end, but we've given away bottom end. So cams are a game of this compromise and trade-off. So as we go bigger and smaller, we gain in one area while we give away from the other area. So when picking one, the goal is to sort of choose one that suits where you want it to be, where you want your power delivery to be, because this is going to be different for each person. Just like some people prefer bigger turbos and happy to put up with the lag. Some people are happy to have big camshafts that have got very little bottom end and so on, but then they've got the trade-off up there at top end. So again, illustrating more again, let's go to this green camshaft, which I've called, say, 290 for argument's sake. Again, it's not an exact thing, it's just an illustration. So look, compared to the other two, we've given away even more bottom end. Okay, so we're really not making much power until, say, a lot higher RPM, 5,000. This is where we're crossing over. And then after that, we're sort of gaining more, and again we're likely to make more peak power, but our peak power points also shifted. So instead of it being, say, 7,500 now, we're somewhere near 8,500, 9,000 RPM. Again, trying to run this on a stock engine with stock bottom end, turning things to 9,000, it may not be very happy. So as you go bigger in the camshaft, your engine needs to be mechanically strong enough, and it needs to be built to take the additional revs that the bigger cam is going to give us. So the other thing to consider with big camshafts and cars is, well, let's think about the gearbox. Your input shaft may not like spinning at 9,000 RPM, and if your engine is. So you go to grab gears and it might fight you, etc. So you may need a more specialized box that doesn't mind spinning at those RPMs for crisp and nice gear shifts. So there's many considerations here. So the typical thing is, what I look at is, I look at what I'm giving away as I go bigger in cams. Am I making that up top? What's the compromise and balance that I'm after for a given engine? And that's the decision that you guys will have to make. What's right for you? What are you chasing out of the engine? How many revs can your engines turn? What are you looking at doing? You're looking at again, this is all, no two camshafts going to be perfect for two different people, two different goals. So you just got to pick the weapon to suit the fight, I guess. And then I've got one last purple curve here, which is to illustrate like a bad trade-off and a bad camshaft choice, where I've called this cam, say, 310, very big for this engine. But in that case, what's happening is, you can see we've given away lots and lots and lots of power only to make this tiny amount of extra power up top compared to, say, our 290. So if we look at the curve again, try to ignore the other lines, but this cam sort of crosses over, say, at about 7,500, 8,000 RPM. And then at 9,000 there, I haven't even peaked yet. It's at 310 degrees. It's at this point with 310 degrees, and it's still going up in the rev range. So again, maybe that camshaft is going to be peaking somewhere around 10, 11, 12,000 RPM. Well, how far do you want to take your engine? Some of these drag engines, yep, they do spin to 10, 11, 12, 13,000 RPM. And, they've got fairly big camshafts to be able to do it. But you got to look at the camshaft in the rev range that you're looking to use your engine. So in this case, for instance, if we were only going to rev to 9,000, because that's all our engine's built for, well, going to this big camshaft here is going to make a slower engine, because although we're going to end up with a higher peak power number there, our overall power through the rev range, etc., it's a lot weaker compared to the other engine. So that's, I guess, the camshaft game. It's a game of compromise, just choosing where you want it to work, a bit like turbochargers. Okay, so in this, again, we've covered about being too big, and then maximum revs that our engine can turn to, what rev range where we want to optimize our power. And okay, let's look at, say, things like VTEC and VVL, and how do these engines work where they got two different lobes on the camshaft. Well, they're basically best of both worlds. So what happens is, imagine like a Honda VTEC or a Neo VVL, the SR20 VE. The best way to illustrate that engine would be, they've got, say, really small camshafts like this line here, and then at a certain point it switches to a bigger camshaft. Let's say our red one there, and then you've got basically a really wide spread of power. There's no compromise and loss of power down low, so you got power down low, you got power up high. It's working everywhere, and that's the advantage of those engines, where, you know, if you can have big cams for top end and the big power, and you can have small cams for the bottom end, for the fuel economy, for the smoothness, for how it runs, and you know, how the engine goes. Those engines are going to be unbeatable. It's very hard to pick one camshaft to do job or two, whereas they've got basically, you know, two grinds on the two grinds that work within that engine. That's going to give it that wide spread of power. Okay. The other thing, you know, is people say, oh, how come, you know, you run, say, 256 inlet and 264 exhaust? Well, or different split camshafts between inlet and exhaust. Look, most engines are designed so that their inlet and exhaust flows are balanced. So generally, same type of duration and lift is required in both, or they're going to be very similar. Some engines where they've got restrictive inlets may need a different cam in the inlet. And then, you know, same with the restrictive exhaust system. You may need a bigger camshaft and a bit more flow in your exhaust side to balance it out. I guess without getting more complicated, the other way is where I split the camshafts and run different is, say I'm thinking between running a 256 and a 264. I can't decide. I might go a 256 inlet, because inlet's the more predominant one that's going to influence how it's going to have the most influence. And then I might go 264 exhaust. So then it's going to end up somewhere between, you know, 256 and a 264. I'm sort of halfway in between. So generally, if you can't decide, then it may be an option to go, you know, a little bit bigger in the exhaust side, and mix them up in that way. You can mix them up. There's no problem. They tend to run, as long as, you know, the difference between them isn't too big. You got to keep them sort of fairly balanced still, because again, we don't want to create an engine where, you know, there's this imbalance in it. Okay, so I hope that's explained some of it. I hope some of this stuff made sense. So on this car, you know, you've seen what's happened. I might actually give this car a run and give you guys a listen as well, how this cam combo sounds. It basically sounds just like a standard engine. Now, that's going to be boring for some people. They want that lopey, choppy idle. That's it. Yeah, well, bigger cams tend to do that. And we should do another video actually discussing why the bigger cams actually get the chop, and what are some of the other considerations that in choosing cams, and why some of this stuff happens. How come bigger camshafts tend to work at higher RPM? We can go into some of that theory as well. It is somewhat interesting, and yeah, happy to do another video on that. But okay, so fired this engine up for you guys, so you can see it's sitting at, I know it's still at cold idle, so it's about 1200 RPM still. But look at the engine, it's basically purring away just like a standard engine. But again, on this engine, we've changed the cams. We've basically got no loss anywhere. We've just made more power everywhere. We managed to tame the big turbo down somewhat by having a little bit more power down low, not making it so much of a hit and a big hard to control when the turbo suddenly comes on boost. Okay, I'm going to turn the car off. I might finish this video here. Just turn the camera around and say bye. Okay, I hope that's been helpful. Any questions, any comments, yeah, fire away. If you'd like to direct messages to ask questions because you don't want to ask publicly, that's also okay. I'll try to answer them all personally. Okay, over and out for tonight. Bye.